Welcome to the fascinating world of units and dimensions, the very foundation of physical measurement and the language of science. For anyone aspiring to excel in physics, especially IIT aspirants, understanding these basics is crucial. Physical quantities are the measurable properties of matter and energy, forming the backbone of how we describe the universe. Every measurement you make, whether it's length, mass, or time, follows a simple principle: quantity equals a numerical value multiplied by a unit. Units act as a standardized reference, ensuring that scientists across the globe can communicate findings with clarity and precision. Without this universal agreement, scientific progress would be chaotic and inconsistent. Let's begin our journey by exploring what makes a quantity measurable and why units are indispensable in every scientific discipline. Now let's dive deeper into the building blocks of measurement: fundamental and derived quantities. Fundamental quantities such as length, mass, and time are independent and irreducible. They form the basis for all other measurements. Derived quantities, on the other hand, are combinations of these fundamentals. For example, speed is length divided by time, and force is mass times acceleration. International System of Units, or SI, is the globally accepted standard, ensuring that every scientist speaks the same measurement language. SI units are defined with remarkable precision based on fundamental physical constants. For instance, the meter is tied to the speed of light and the kilogram is anchored by the Planck constant. This precision guarantees that our measurements remain consistent and universally valid, no matter where or when they're made. Dimensional analysis is a powerful tool in physics, serving as both a sanity check and a problem-solving technique. Every physical quantity can be expressed as a dimensional formula, using symbols like m for mass, L for length, and T for time. For example, the dimensional formula for force is MLT2, showing its dependence on mass, length, and time. This method helps verify that equations are dimensionally consistent, a must for any valid physical law. Beyond checking equations, dimensional analysis aids in converting units and deriving relationships between quantities. It's especially useful when dealing with complex calculations or unfamiliar systems of units. Mastering this technique not only prevents errors, but also deepens your understanding of the underlying principles that govern the physical world. Let's look at how dimensional analysis is applied and some intriguing facts about units. This technique is more than a consistency check. It's a gateway to solving complex problems, converting between unit systems, and even deriving new relationships in physics. For example, the ampere and mole have precise definitions rooted in physical constants and fundamental properties. The naming convention for units honors scientists, with unit names in lowercase and symbols capitalized. Understanding historical systems like CGS, FPS, and MKS is also important for context, as they still appear in older literature and some engineering fields. These insights not only enrich your knowledge but also prepare you for advanced problem-solving and cross-disciplinary communication. Summary: mastering units and dimensions is non-negotiable for anyone serious about science. They form the universal language that enables precise communication, collaboration, and innovation across the globe. Dimensional analysis acts as a fundamental check, preventing errors and guiding the discovery of new physical laws. Whether you're solving IIT-level problems or exploring the frontiers of physics, a solid grasp of these concepts is essential. Remember, every scientific breakthrough relies on accurate measurement and clear communication, skills rooted in the understanding of units and dimensions. As you continue your studies, let this foundation empower your journey into the deeper realms of science.